Okay, so let me show you something interesting. First, an exercise. So exercise. So practice the law of total probability. So in a box, you have 10 coins. 6 fair and 4 biased. Okay, so biased means that the probability is equal to 2/3 of heads. Okay, so now consider the following 2 experiments, and we're interested in the probability, the chances that you flip 2 heads. So probability to flip 2 heads. And here are the 2 experiments. The first experiment is you pick a coin randomly. A coin randomly and flip 3 times. And now we want to know what are the chances you got 2 heads. Use the total probability to solve, use the law of total probability to solve it. And the second question is, you pick a coin, you flip 3 times. Okay, so you flip 3 times, just like before. Flip 3 times. But each time, for each time pick a random coin, okay, flip it, and then put it back into the box. Okay? So it's important to understand the difference between these 2. In the first case, I just picked a coin once. I randomly picked a coin out of these 10, flipped it 3 times. In the second case, I pick a coin, flip it, put it back. Now randomly pick again, flip, put it back. Randomly pick again, flip, put it back. So analyze these 2 experiments. Okay. Meanwhile, I'm going to show you something very interesting. Well, when I say that, I mean interesting for me, right? I hope it's interesting for you. Okay, so your friend comes to you and says, let's play a game. Okay, heads I win, tails I lose. And I've got a coin. And now you suspect this guy, he's taken Fox. Maybe he's got a biased coin. Okay, so, friend has biased coin. Question mark. Maybe, you don't know. You'd like to trust the guy, okay, but, you don't know, okay. Is it going to be a fair coin? So, what you're going to do is instead of putting the guy on the spot, putting your friend on the spot, you propose, okay, let's play heads I win, tails I lose, tails you win, okay? And we'll use your coin, which I'm gonna, which I'm gonna sort of trust is fair, but I'm gonna somehow manage to ensure that it is fair. Okay. So, is it possible to create a fair coin from a biased coin? Question. Is it possible to create a fair coin from a biased coin? Okay. Without knowing that the probability that the coin flips heads. Okay. Without knowing the probability coin flips heads. Okay. So let's call the probability that the coin flips heads, let's call it P. So idea for a fair coin, P is a half. So P equals probability to flip heads. Okay. So here's my suggestion. Okay. You don't flip the coin once, you flip the coin 2 times. Okay. Now in the first flip, the coin can either turn up heads or tails. Okay. The problem is you don't know what the chances of heads are, and so you don't want to be done here because what if, P is very high and then, your friend is winning all the time. So this could be P, and you don't know what P is. We will assume that it's not 0 or 1. Okay. So it's not a deterministic coin. It has randomness. Okay. So P. And this is going to be 1 minus P. Why 1 minus P? Because these 2 must add up to 1. Okay. Now, flip it again. Okay, so if you flip it again, this is P with going to be heads, 1 minus P, it's going to be tails. Okay, and if you flip it again, in this case, it's going to be heads with probability P, and tails with probability 1 minus P. Okay, good. Okay, so these are the outcome, and let's see. So the outcome is, heads, with probability P squared, heads, tails with probability P, 1 minus P, tails, heads with probability P times 1 minus P times 1 minus P, 1 minus P in that case. And here you get tails with probability 1 minus P 1 minus p. So 1 minus p squared. Okay. So now here's the idea. Look, heads, tails, and tails, heads has the same probability. Okay. So what we're going to do is we're going to say if you flip twice and it's heads, tails, we'll count that as a heads. So we'll count this as, I'll call it a heads. I'll put it in blue heads. Okay. And if it flips tails, heads, then we'll count that as a tails. And now what we know for sure is that the chances of heads and tails are exactly the same independent of p. Okay. Now, what do you do in the other cases? In the other cases, what we'll say is we restart. It's a foul flip. Okay. Foul. Restart. Okay, so foul. Restart. Now, you see that it's possible that this coin flipping to just get one heads or one tails could go on forever if you just always flip heads. Okay? So this is an example, just like in the last lecture where we were flipping a coin till you got a head. This is an example of an experiment that may never end. Okay? You could arbitrarily keep going tail, tail, then head, head, then tail, tail, and keep restarting. Okay? But when you stop, it'll either output heads or tails. And it sounds like the tails and heads will be output with equal probability. So now we've constructed a fair coin from a biased coin. That's like a miracle. I don't even need to know the bias. Okay, so let's prove it. And we're going to prove it using the law of total probability. You could also just analyze, just like we analyzed last time, you could analyze the infinite tree of possible outcome sequences, but it's much cleaner to use the law of total probability. So here, the probability of heads is equal to, okay, now it turns out that unlike, the standard law of total probability with 2 cases, there are 4 cases. Okay, there are 3 cases. Either you get heads, you get tails after 2 tosses, or you restart. So it's the probability of, probability of heads is equal to the probability of heads given heads, tails, okay, times the probability of heads, tails, plus the probability of heads given tails, heads, times the probability of tails, heads, plus the probability of heads given restart, times the probability of restart. Okay, so now let's see if we can put probabilities to all of these. The probability of heads given heads, tails, probability of heads given heads, tails is 1, because you're outputting heads, so this is 1. And the probability of heads, tails, this is p, and 1 minus p. Okay. The probability of heads given tails, heads is 0, because you're outputting tails, and you're stopping. Okay. Time, whatever this is irrelevant, this is p, 1 minus p. Okay, but now comes the interesting case. The probability of heads, given that you restart, times the probability of restarting. Well, the probability of restarting is p squared plus 1 p times p squared plus 1 minus p squared. So this is p squared plus 1 minus p squared. Okay. Now, what's the probability of heads given restart? Well, if you restart, the chances of heads are exactly the same as the chances of heads at the beginning of the experiment, because that's what it means to restart. So this is exactly the probability of heads. Okay, so what do we have? We have that the probability of heads is equal to p times 1 minus p, okay, times 1 plus 0 times something, which is 0, plus p squared plus 1 minus p squared times the probability of heads. Okay. So we actually didn't compute this. What we have done is we've gotten an equation for this guy in terms of itself. That's what the law of total probability allowed us to do. Okay, and we can solve this equation. If we take this term to the other side, we find, and I leave you to do the algebra, take this to the other term, and then you'll get 1 minus this coefficient, then divide both sides by that 1 minus this coefficient. You get that p of h is equal to p times 1 minus p divided by p squared plus 1 minus p squared. And you can do some algebra, okay, to show that this is exactly p, 1 minus p, divided by 2p, 1 minus p, okay, which cancels. This is 1/2. As suspected. So this mechanism converts the biased coin. It may not be biased, but you don't need to now put your friend on the spot. It may or may not be biased. I don't care. This prescription, you do this experiment, and when it stops, it'll output heads and tails, and the probability of heads is exactly 1/2. We have converted a biased coin into a perfectly fair coin, provably fair. And so this is a mechanism you can use with any coin because, all coins are somewhat unbiased. And this guarantees that so all coins are somewhat unbiased because of physical imperfections. And this guarantees that you convert it to an unbiased coin, to a fair coin. Miracles of probability. Okay, checking out. See you next time.